So today we are going to talk about some of the technologies that are around us, and we want to see whether they are part of us or how they can be part of our work as well. Let me just say that if you look at structural engineering from a very sort of high level philosophical standpoint, this is basically where we deal with some cause, effect, and mitigation. So there are some causes, for example, natural or man-made hazards that changes with time. And there are some effects due to those causes like deformation, stresses, and so on. And our job is to mitigate those effects through design and detailing, and then control them through various means. So that's roughly, I would say, a role of the structural engineers generally is. Whatever we do, more or less falls within this broad spectrum. So how do we do this? If you just step back a little bit, then we can see that we can do this in a number of ways, because you know very well that people have been building and constructing very complex structures for hundreds and thousands of years before computers, before mathematics, before anything. So that means there was some way that they could do this. They could mitigate those effects or estimate those effects through intuition, through estimation, and so on. And then, of course, we have pure mathematical equations that came along. We have the rational procedures that came along. They can be applied to certain cases in some form. And then after that, we have the combination of procedures and rules, plus some mathematics combined together as we learn. And then we also rely a lot on previous experience, both good and bad. So roughly, we do our job with a combination of these in practice. We learn some of these things in classrooms. Some of these we learn during practice. Some of this is learned through other people sharing their experience. If you think about it, the old time trades were passed from generations, one father to son, because these were experience that had to be conveyed, because there was no formal procedures or process or computers or programs that could help at that time. So let me take you back to your first undergraduate class somewhere where we were taught on how we can analyze a simple beam. And if you have a beam like this, then you could calculate the bending moment and the deflection, and the formulas were very clear. You could just use that formula, or you can use that formula. And you would get these results no matter what, and you didn't even have to know what kind of material is this? Where is this located? What is the purpose of this beam? It's a bridge, the building, it doesn't really matter. It's just an idealized structure. And you have been given some, in fact, the dimensions are also not important. All what is important is E and I. And once you have that, you could compute the deflections. And for calculating moment, even that is not important. So beam could be very deep, very short, it doesn't matter. We will get the same answer. So the mathematical solution to the cause and effect in this particular case is rather simple and straightforward. And there is no two ways about this. Let's see, next we think about to mitigate this bending moment or deflection is too much. So we are supposed to make sure that we control it. So we have to design the section to ensure that this bending moment that we're getting will not cause undue response. So before we can do that, then we have a lot more questions to ask and answer. What kind of design code do we want to use? What type of load is it? Dead load, live load, moving load? What type of concrete it is? What is the strength? What is the characteristic of the concrete? What type of reinforcing steel are you using? What is the cover? What bar sizes are available? And so on. Suddenly, now the problem, which was very simple, becomes a little bit more complicated, and we have a lot more data, a lot more subjective things coming in before we can answer that simple question of calculating reinforcement in the same section. And now no longer it's a simple mathematical equation. We need now to have more knowledge, more understanding, and practicality comes in also. Availability of the bar sizes comes in from the market. So suddenly the problem now becomes far more complex, although not very complicated, but definitely more complex than before. So let's say we do that, and then we do the calculation based on ACI or whichever method we use, and we come up with some area of steel. Then after that, we actually could yield different answers for the same amount of reinforcement. So we could use 6 bars, 4 bars, or 3 bars, depending on what sizes we choose. Each one may give us a different final outcome. So now the cause and effect and the final design are not really directly related because we have now got some approximations, some judgment, some other factors coming in, and now we have altered the equation. So it's no longer a direct path to this one, and there could be multiple answers, and each one of them will still be okay. So this is how the design, I would say, differs from pure science or mathematics. And the question is, could an experienced engineers have done this design through intuition or design sense without doing any calculation? If I look at my own practice very, very long time ago, when I used to get a project, especially not very complex ones, once I get the project, I will start making the drawings and start putting the reinforcement and even start writing the bar sizes and number before I did any calculations. And then give it to the drafts person and they will start drafting it. This is before CAD, this is before computers, before everything. I'm talking about something in 1982 or 83. And then while they are making the drawings and while they are completing the drafting, I would then start doing my calculations and simply confirm or not confirm what I have already assumed in the design. And most of the time, my estimation would be correct. And the reason is because it was trained. It's just like driving. When you learn to drive, you can overtake a car. You don't need to calculate the distance between them. You don't need to calculate the speed. You just know when it is safe to do that. And some drivers are more courageous than the others, so just like some designers are more courageous than the others. That's how a design sense would develop. And we would have an intuition to do the design without doing any calculations. And a lot of engineers I know at that time, and I'm sure some of them are also in the audience of that time, we used to do this, most of the work like this, because we didn't have a choice. Time was not enough, and we just had to produce answers quickly. So intuition and experience learned and reinforced gave us this ability to do the design rather quickly using a design sense and intuition. Then let's talk about just another step in the checking of the serviceability of the same beam, let's say deflection, and how to mitigate that. So when we do the deflection, now a lot more questions come in because now the deflection that we determined from the formula is no longer reliable. It's not even remotely accurate for the beam, especially for a reinforced concrete beam, because the environmental conditions, the nature and duration of loads, the purpose and use of the beam, and at what time the deflection will be needed, because long-term effects will come in, creep and shrinkage will come in, and humidity will affect it, and so many things, and aging of concrete will affect it. So the whole scenario now changes. The deflection on first day will be different from deflection in 5 years. And that also will depend on when the live load was applied and so on, and how the formworks was released, and did we have a camber or not. So now just a simple matter of calculating the deflection, it actually becomes very complex. And no matter what deflections you compute is going to be unreliable because it's hard to estimate all of the factors that affect the real deflection. So it's just going to be a good range that you can estimate. So, which means that now we are moving farther and farther away from purely deterministic answer to our simple beam. And because the E is not known, the I is not known, it depends on cracking, it depends on age, it depends on so many things. So the deflection is not known. And deflection could range anywhere, and deflection could be off by factor 2-3 times, not just 20-30%. So that's how much variation in the deflection determination of a simple beam can be. So which means pure computations here do not really give us a very reliable answer of the things that we're doing in. Reliability, of course, could be improved through lab testing and calibration, and also through measuring of the beams during their life. And many people do that. Now, many structures have inbuilt sensors, so we can measure these things while the structure is in service. So we get this feedback, and we can now correlate that to the computations and so on. So we rely more on measurement than computation for some of these responses, especially those related to serviceability. Let's go back one more time to our computational development. So once you have more than one actions and more than one results, then we develop the matrix analysis. And in this case, for the beam, we developed the equations. So we developed a relationship between 4 variables and 4 input and 4 output through this matrix, and all of which can be computed by the beam properties. So if the loads are known, the beam properties are known, we can calculate the deflection. Let's say that the loads are known and the deflections are known, like in the case of measured response. So which means this matrix is no longer known now, because these are real on the right-hand side and left side are also real. So whatever the matrix in between was originally is actually not reliable, not correct. So which means that now we could determine this matrix by looking at the input and output in the reverse order, and then use that updated matrix, and then use that again to correlate the input and output with the matrix that we have determined from the previous experience, and use that experience to determine new values. So this was what we will call the artificial neural networks will come into play. So why is this possible? For the simple reason that as engineers, we don't have to have 2 + 2 = 4. The number of bars may not exactly match with the amount of reinforcement we compute. So we are okay with 3.9 to 4.1. So that means we can use this assumption and this variability in the results to determine those matrices that will link this data. So we can use the artificial neural network, which is the basis of most of the AI, in which we have those hidden layers, and then we have the input and output, and those hidden layers could be determined through a lot of known input and lot of known output, and then what we call a training of the network, and we use that network then to solve similar problems where the output is not known, only input is known. This is the way we could use artificial intelligence kind of for doing things for which direct determination is not reliable, or exact determination is not even needed or desirable. So this is how we can step back to our experience of learning and use that to make the estimations. So let's look at tall building now. If I say that this is a 50-story building, 190-meter high, and what would be the natural period of this building? Most of you would have some answer because the codes give it, and you also have some experience. Somebody will say number of stories divided by 10. Somebody will say height divided by something. And we could come up with a result of 3 to 6 seconds, depending upon which formula we use. How do we do this? Because we didn't do the eigenvalue analysis or any of those finite element yet. We just look at the number of stories and height, and we say, okay, this is the natural period, but the range is still very, very big. And this is a critical number. We cannot have such a big variation in our acceptability. You know very well that this can be computed, and we can determine all the modes, and we can determine the mass participation, and we can determine each direction and everything through the software that we use. The answer still remains, is it real? Is this number really representing the real buildings? Because this is based on a model which may have significant shortcomings, as I mentioned to you earlier. People have been measuring the buildings. This is, for example, 200 buildings measured in China, and that is the plot of those buildings, natural periods, and they have been trying to determine graphs to represent this data. So which means now we are going back to the data from real buildings to calibrate or to check our computation, which is based on sophisticated finite element analysis. But we can't rely on it because we have seen that there's a difference between that and what we find in the field. So this data that we are calculating, that we are determining, actually now this data and other data could actually become the future way of doing things. Rather than going from left to right, we could go from left and right and back in the middle. So we could do this for a number of different variables, not only natural periods. What if we use this concept, this idea of using the experience learned from the field or from the previous design and extended it to determine more quantities, not just natural period, and not replace formal calculation, but supplement the formal calculations using the same concept. Of course, in the past, when there was no computers, those of you who work we used to carry handbooks, and these handbooks had graphs in them, hundreds and hundreds of pages of charts and graphs to design columns, interaction diagrams. And so basically what they had done was they had designed thousands upon thousands of columns by hand or by another procedure, and then drawn graphs for people to go and search and find the one which matches our real case. Same set of data, same designs that we generated easily could be packaged into a box, so to speak, which will do the same thing. Instead of you searching from all the pages in a handbook, it will search the right location, right curve, right parameters, and give you the reinforcement that you need based on the moment and exit load that you specify, and so on, based on the cross-section size that you specify. So it's the same thing that we have been doing before, but just in a more organized and more systematic manner, where we can search through data and find the answers where we cannot do the computations, or we cannot do them reliably or fast enough. Exactly the same what we have been doing for a long time. Now we have the opportunity to do that in a systematic manner, something called AI and ML and DA. Using AI in structural design process is basically to jump over steps and go from the input to output and not worry about how it is done. So for example, you get the architecture design, and from there you directly jump to code-based design or even performance-based design, and you skip everything in between. And this is possible because we have been doing this. As I mentioned, the design handbooks were exactly like that. And we have been doing it intuitively before the computers in any case. So people have been doing it. It's only last 50 years that we have these tools available. So we could use these tools to reinforce what we already have been doing hundreds of years before that, and do it more reliably or more systematically. And this is where AI and all of these technologies could help us. For example, we could determine the efficiency of the building and see whether the building's layout or system is efficient or not in terms of the structural area usage. That means shear walls plus column area, we have divided by floor area. This ratio is very critical because it tells us how efficient our structural system is. The smaller the ratio, the better it is. But it will depend on many things. So what should be the ratio for a particular building? It's hard to say because it depends on seismic zoning, it depends on the height of the building and many things. But if we have enough data from the design which we have, we could predict this and check whether we are doing an efficient building or not. The ratio, for example, from some of the data that we have is varies between 12% to 2%, as low as 2%, as high as 12%, mean is 6%. But where should your building be? So once again, this is an opportunity where data can come to help us to help us optimize and make our buildings efficient and check whether we are doing an efficient design. Similarly, we could estimate the quantities quickly only based on these parameters that have been predetermined from previous buildings. Of course, many engineers know these numbers by hand or by heart already from their projects, but they are averages. They're not intelligent averages. They have to be more specific to type of project. So that can be done if we crunch those numbers, and if we have the numbers for each type of structure, height and size and code and seismic zone and so on. So we have an opportunity to actually look at the entire structural engineer's workflow, conceptual design, modeling analysis, and design and detailing, and then find opportunities where we can use artificial intelligence, machine learning, and data analytics. So I can see that almost every step, except maybe probably in pure analysis, where we have finite element anyway, we could use these tools. And engineering judgment is being used. So wherever we use our engineer's judgment, it could be aided by AI, because fresh engineers may not have the same level of expertise or confidence on their estimate as experienced engineers. How can these emerging tech developments help to make these structures better designed, more efficient? with improved performance and higher resilience and sustainability? The answer is to use these technologies effectively. And that is to make the process easier and efficient, whatever we are doing. And also to create a better system and a better process. Things that we are not doing, we can be doing now, because now we have opportunities to do them in a different way. Structural engineers need to be the cool heroes who will save humanity using new techs, because we basically, if I borrow the words of Mr. Ashraf, we are the people who save lives. We are in the business of saving lives through our designs. So if we do that also using new techs, then it will be even cooler. For example, we could be making headlines like this one. The AI is helping scientists predict when and where the next big earthquake will be. True or false, but this is a headline people would like to see. So if we do something which is significant for the public, and it's also using high tech, it will definitely catch public's eye. So I think all of you are familiar with the industrial revolutions, and we were saying that now we are in the fourth industrial revolution, Internet of Things, AI, big data, cloud, cyber physical systems. This is supposed to be today. So let me ask you this question. How many of you really believe that structural engineering is already here in today? How much are you every day using these tools in your work? Just look at your work and workflow and your colleagues around you and see, are we really here today where the rest of the world is supposed to be? Because when I look around, I hardly see this, that we are using these technologies enough compared to other disciplines. And world is already moving on to the fifth industrial revolution. And we have to catch up to at least be on the fourth level. And the singularity, as people say, is approaching, not too far, according to most estimates, when this machine learning, machine intelligence, human intelligence will intersect, and then machine intelligence may surpass human intelligence, and we will have this transhuman concept. So according to specialists, this is not too far away. So we should go back and at least look at these three technologies and see how we can use them and how instruction engineers are using them. Let me just give a quick rundown on what these are, and then we will go back to their applications in engineering. So basically, all of these are parts of data science. And data science is based on data mining. It's all based on data, which is, we have lots of data now, as you know. Data is everything. Data is the new gold, as I say, because you can use data for doing almost everything, and people create whole businesses based on data. So the whole idea of data, using machine learning, using artificial intelligence, using deep learning, all of that, the neural network, intelligent agent, the systems to use those data have already been developed well. For example, machine learning, supervised learning, unsupervised learning, reinforced learning, the people have been working on it, and the methodologies are all there. We don't have to develop these. These are already being developed or have been developed by the computer science people and other people working in this field, and mathematicians. Artificial intelligence is a combination of many things, many paradigms. I remember in the 80s, expert systems were very common as form of artificial intelligence. They just mimicked thinking of an expert and tried to copy how an expert would make decisions and put them into decision trees. And I did some work on them a long time ago. And same is the case for other things. But now all of these things have been fused into a whole new discipline. And so artificial intelligence is not new, started somewhere in 50s, and now it's moving on to deep learning. And now we are able to do bigger things in a more general manner and in a more diverse manner. But I still feel the structural engineering has not really benefited from it as much. So if you look at artificial intelligence, machine learning, deep learning, the difference is in the way the neural networks or the programs work inside. It's a detail that we don't really need to be aware of to use it, because as I mentioned, the technologies have already been developed. The methodologies have been developed or being advanced every day. All we need to do is to understand them and to be able to use them to our benefit. Another recent trend is using of the decision trees, which is, like I said, it's like an expert system. It takes the data and makes the decisions on where next to go. And it's part of the learning methodologies many programs use. AI could be broadly categorized into two. One is the weak AI or narrow AI, and one is the general AI or AGI. And people are using the narrow AI for a long time for many things, many things for many years. Playing chess, for example, is a narrow AI because it just does one particular thing very well, even beats humans on that. Self-driving cars, which is very complex, is still narrow AI because it's doing one task. Same system cannot play chess. And the system that plays chess cannot drive a car. But a human being can do both. So that is a general AI. That means an AI which can do multiple things with the same level of sophistication. Like robots we see in science fiction, that they can serve people, they can communicate, they can save people and so on. And we are now, people are worried about when AGI becomes predominant, will it take over humans and so on? So that's another worry altogether. And a lot of people are doing research on that. So it's for that not to happen. But right now, we are not even, structural engineering is not even at the weak AI level yet. So machine learning, basically, if you, those of you who do computer programming, you know very well, for a computer program, we have input data, we have a program code, and then we have a computer, we program it there, and then we get the output. So we put the input, we use the program code, we get the output. But in terms of the machine learning, we give the input, we also give the output, and let the computer generate the matrices or the linkage or the code. And that's how the machine learning is different. And that's how the machine learning can continue just because we have data. And then IoT, very important, because we have sensors everywhere and they generate data all the time. If we just connect that data properly and link it to the AI systems, then we can learn a lot and make many decisions based on that. So big data, which is just the amount of data, people say that we generate in a day is more than what was generated in thousands of years before that, because of all these sensors and all these devices which we have going on. Anyone who drives a car knows very well how much AI or how much data these cars generate and show you. To summarize this whole thing, data science and all of these tools are just tools. They have no meaning without business domain knowledge. Without this, computer, AI, mathematics, data science will be not meaningful. It has to do something, and that something has to come from a business domain. And if that business domain is structural engineering, then we can utilize the same algorithm, same system that any other business domain is doing, and we can benefit from it. Medicine is doing it, transportation is doing it, structural engineering can also do the same thing. Just get into this matrix. So we have to now develop processes that use these technologies. We have to rethink, how can I do it with data? How can I do it with AI? How can I do it better and not always turn to the traditional formulas or procedures that we have been doing for so long, because there is an alternate way that everyone else is using. So let's look at some examples. There are many examples. Actually, I shouldn't say many. If you look at the internet, you might not find as many as you imagine. So there are some levels that you can find. You can find AI in planning and conception and modeling and somewhere. So yeah, there's some of the metrics. This number doesn't mean the number of applications we found. It means the level of adoption in those different stages of our work and different technologies. So this is just a rough metrics based on the internet search of the sources that you can find. So you can see here that still the conceptual planning, they get a lot. Monitoring and construction get a lot of these technologies. And these are some of the things that you can find, but not a lot on the internet.